guidance. We have climatology and persistence, and that's sort of built into what we use the SHIPS model, which is the statistical hurricane intensity prediction model. Within that model, there's a number of predictors. Those predictors include the day of the year, where the storm is located, how fast it's moving, what are the sea surface temperatures underneath it, and along the forecast track, the ocean heat content, the atmospheric shear, and its direction, a wide variety of parameters. And we heavily rely on this. In recent years, we have been using the dynamical models. We do have output from the GFDL and the HWRF, but what we've found is after conducting a study is that there's not much skill there, because when you take out land effects, the skill is essentially zero. And we try to form a consensus also, since the consensus tends to work very well. We have a consensus forecast, the ICON, which is an average of the GFDL and the SHIPS model. But notice in this case, this is the verifying intensity for a particular system. Look at the forecast for intensity. They're far under what they should be, and we do not do a good job at all in trying to in predicting rapid intensification or rapid weakening, for that matter. And here are just a few more cases with Dean. Notice that with regard to the intensity guidance, that they rarely, if ever, capture the true intensification that takes place. And this is something that we are striving to work on, but we don't have a solution for it just yet. This is another, let me go back to that. This is another example with Felix. Again, the intensity guidance severely lags what really happens in real life. And especially for this one period here where Felix basically went from a tropical depression all the way up to 150 knot hurricane within a matter of a very short period of time. So with regard to intensity forecasts, this is what we consider. The considerations are the same as with the track forecasts. The National Hurricane Center intensity forecasts tend to be very conservative, and we rarely, if ever, forecast rapid intensity changes because we just don't think that we have the skill. And so if there are changes in sea surface temperature or vertical wind shear along the forecast track, that's primarily what we look at. Those are the primary factors that we consider to determine our intensity forecast. And they're also based upon the guidance from the SHIPS and the GFDL model, which taken together become the ICON consensus. So finally, after all of this, again, we coordinate the forecast watches and warnings. Here's an example of what we look at when we sit down to try to determine where the warnings should be. These are the various breakpoints along the coast, and we will determine which of the breakpoints is where we should start or stop the warnings. And in general, because of our forecast error, the size of the warning is going to vary. It's going to vary with respect to the forecast track, the size of the storm, and the known uncertainties in the forecast track. This is a really good example here at the bottom. These are some average statistics. The average storm total watch length is generally about 490 miles. And the total that the part of the coast that actually receives hurricane force winds is only about 100. So if we issue a watch, only about 20% of the coast actually sees hurricane conditions in the end. And the average lead time associated with the watch is 50 hours. And when it comes to warnings, it's a little better. You notice that we end up warning over a slightly smaller area, and about the same part of the coast gets those conditions. So about 25%, there's a 1 in 4 shot of observing hurricane conditions. The lead time is about 34 hours. Not this year, but next year, we're increasing the lead time. We're actually already doing this in-house, but the definitions of a hurricane watch and warning are going to change. We're going to have 12 hours of additional lead time. So how does this become a factor? Well, it does in the sense that the forecast of size and the subsequent wind field will determine where we place the watches and warnings. And this is an example with Katrina. And you notice the red area here, which is where the hurricane warning was, we just barely, notice here on the east side, the hurricane force winds actually extended out just as far as that. We don't like to cut it that close in general. But then you look at a case with Charlie where the wind field was very, very small. And someone might call this an overwarning. But the orientation of the forecast track with respect to the coast does play a major role in how we determine the size of the warning area. So I wanted to show you this in conclusion. These are our typical track errors since 1990. You notice that they've been cut in half since about that time, almost at